Have you ever stopped to think about what language your phone and your computer are actually speaking to each other? Well, today we're going to pull back the curtain on this secret language that powers our entire digital world. It's called Boolean Algebra, and it's this incredibly simple, really elegant logic that's running inside every single piece of tech you own. So let's dive in.
So, let me just ask you this. What's the one language that your phone, your laptop, every server at Google, and even the most advanced AI, what do they all have in common? It's not Python, it's not C++, it's not English. It's the language of pure logic.
You know, the story of this language really starts with two brilliant minds, separated by almost 80 years. First, you've got George Boole back in 1854. He's a self-taught mathematician who comes up with this purely theoretical system for reasoning with just true and false. He never even saw an electronic device. Then, fast forward in 1937, an MIT engineer named Claude Shannon has this huge breakthrough. He realizes you can build Boole's logic using simple electrical circuits. And that connection, that single idea, that's the moment our digital world was born.
Okay, so here's our game plan for today. We'll start with the core language of logic itself, then we'll break down its basic building blocks. From there, we'll get into the rules of the game, see how simplifying things makes our world faster, and finally, we'll talk about why this math is still so important today.
All right, first up, the language of logic. The most important thing to get here is that this isn't just some abstract topic for a math class. No way. This is the absolute bedrock of all digital systems. I'm talking about the processor in your computer, your PlayStation, the decision-making in an AI. It all boils down to this really simple logic.
So how does it all work? Well, that brings us to the basic building blocks. And you have to understand, everything, and I mean everything, starts with one incredibly simple idea, thinking in just zeros and ones.
At the very heart of all this is something called a Boolean variable. Now, unlike the variables you remember from school that can be any number, a Boolean variable can only be one of two things. It's either a 1, which means true or on, or it's a 0, which means false or off. And computers just love this system because it's so easy to represent with electricity. Is there voltage? Great, that's a 1. No voltage? Okay, that's a 0. It's simple, it's reliable, and it is unbelievably fast.
Okay, now let's look at the first of three basic operations, the AND operation. The rule for AND is super strict. It will only give you a 1 or true when both of its inputs are 1. If even one of the inputs is a 0, the whole thing becomes 0.
This chart here is called a truth table, and it makes that rule crystal clear. You can just see every possible combo. 0 and 0, you get 0. 0 and 1, still 0. The only way you get a 1 at the end is if both A and B are 1.
And here is a fantastic real-world way to think about it. Imagine two light switches wired up one after the other. For that light bulb at the end to turn on, the electricity has to get through both of them, right? So you have to flip switch A and you have to flip switch B. If either one is off, the circuit's broken, no light.
Next up, we have the OR operation. Now this one is way more relaxed than AND. It outputs a 1 if at least one of its inputs is a 1. It doesn't care if it's the first one, the second one, or even both of them. And you can see that in its truth table. The only way to get a 0 is if both inputs are 0. Now, you're probably looking at that last line and thinking, wait a minute, 1 plus 1 equals 1? And yeah, in Boolean logic it does. Just think of 1 as meaning true. You can't get any more true than true. It's the highest possible value you can have.
The analogy for OR is just as good. This time, imagine the switches are wired in parallel, so the electricity has two possible paths it can take. All you need to do is close switch A or switch B, and boom, the circuit's complete, light turns on. And of course, closing both works too.
And the last of our basic building blocks is the NOT operation. This one is the easiest of all. It just takes one input and flips it to its complete opposite. So if you give it a 1, it spits out a 0. If you give it a 0, you get back a 1. Simple as that. It's the logical opposite day operator.
So, now we have our building blocks, AND, OR, and NOT. But we need some rules for how to play with them. That brings us to the rules of the game. And I want you to think of these not as some boring laws, but as a really powerful toolkit for messing with and simplifying logic.
So here are some of the most fundamental ones. The identity laws. They basically say that ORing something with a 0 or ANDing it with a 1 doesn't change a thing. Then the null laws show that ORing with a 1 will always give you 1, and ANDing with a 0 always gives you 0. And the complement laws are really cool. Any variable ORed with its own opposite is always true, or 1. And AND it with its opposite, always false, or 0. Now this one, De Morgan's law, this is a real power tool. It tells you how to deal with a knot that's applied to a whole group of things. What it says is, you can kind of push the knot inside to each piece, but, and this is the important part, when you do that, you have to flip the operation. So an or becomes an and becomes an or. This little trick is absolutely crucial for simplification.
And that whole idea of simplification brings us perfectly to our next part, simplifying for a faster world. This is where we connect all this abstract math stuff back to the real world and see why these rules are just so incredibly important.
Okay, so here's the big connection. Every single part of a Boolean equation, every and, every or, corresponds to a tiny physical switch on a computer chip, what we call a logic gate. So the goal is always to make the equation simpler, to have fewer terms. Why? Because fewer terms means fewer physical gates have to be built. And fewer gates means the final chip is cheaper to make, it runs faster, and it uses less power. This isn't just a math puzzle, you guys. This is the absolute core of modern hardware engineering.
Let's actually see it in action. Take this expression A and B, or A and not B. Looks a little complicated, right? But watch. First, we can just factor out the A since it's in both parts. That leaves us with A ANDed with the group B or not B. Now remember that complement law? Any variable ORed with its opposite is always 1. So that whole B plus B part just becomes a 1. Our expression is now just A and 1. And finally, the identity law tells us that anything ANDed with 1 is just itself. So the entire complicated thing simplifies down to just A.
I mean, just think about what we just did there. We took a logical idea that would have required 3 physical parts on a chip, 2 AND gates and an OR gate, and with a few simple rules, we proved it's exactly the same as a circuit that needs just 1 part. We literally made it 3 times simpler, 3 times faster, and 3 times more efficient, just by using a little bit of math. It's incredible.
And that leads us right into our final section, why this math still matters. Because this isn't some dusty old historical topic, it is a living, breathing language that's used by engineers every single day.
As one of our sources put it so well, Boolean algebra is the language of digital systems. Every CPU, microcontroller, memory chip, and logic gate is built from these rules. It really is the invisible architecture holding up our entire technological world.
When you think about it, it's just an incredible journey, right? From a purely abstract idea in the 1850s to the engine driving the 21st century. And it really makes you wonder, if this simple system of true and false gave us everything from smartphones to artificial intelligence, what will the next generation of engineers and thinkers build with it? Thanks for joining me on this one.